we've got the final component of Lab 1 is due this Friday. Has anyone finished it? Hopefully Part D, right, Delta? So the Part D, the final component of Lab 1 is involves a fairly significant step up in difficulty level compared to the first three, which you might not expect since it's part of Lab 1. And so today I'm going to do a demo where I'm going to work out a solution to a sort of a comparable problem to help you out and show you what methodology I follow to solve that problem. So Part D is to implement software-defined UART, to bit bang the pins in order to implement one side of a UART connection. Just transmit, right? UART transmit.
We're only doing transmit.
Yeah.
Receive is harder because you'd have to find a way to catch the clock edges, and it can be done, but it's tricky. So
you're going to be doing UART receive in software. So I thought, well, how can I do a demo that illustrates that without actually doing it? And I thought, well, why not do a software-defined SPI, which is pretty similar to UART, and then work that out, especially since it works out. It's nice because we just got done talking about SPI last lecture. Okay? So as you remember, we've got SPI is synchronous. There's a clock that's driven by a master, and there's a one bit that comes out of the master called master out slave in. That is the way that the master sends bits to the slave, and then the slave also sends bits back to the master with the master in slave out. So master out slave in is MISO, and master in slave in is MOSI, right? And then there is a slave select that is driven low to indicate when a transaction is happening. Last time I talked about how to do this using the hardware support for SPI. And in that case, if you're on the slave side, you have to set up what word you want to send back to the master before the master initiates the transaction, right? Is the way it works with the 328. I also mentioned that we're actually not going to be using it as a slave device. We're going to be using the 328 as a master device, and the slave is going to be the accelerometer, right? Okay, so there's also this notion of CPOL and CFA, which CPOL just defines what state the clock is in when it's idle. So CPOL 1 means the clock is normally high, just like the slave select is. And that's the mode that's used in the accelerometer. CFA is a little bit harder to describe, but the idea there is if CFA is 1, which is shown at the bottom here, it basically means that the bits are transacted not on the first clock edge, but on the second clock edge. You sample on the second clock edge as opposed to the first. So CFA is a phase shift of 1/2 clock cycle. Right? You guys with me? Okay. So so how can we what's a good way to build out a software SPI? Well, I thought, well, how about we implement an SPI master in software, and then we can use the hardware, the SPI hardware, in slave mode, and that way the chip can talk to itself. We can have the software being a master, and we can have the existing coprocessor on there be the slave, and it works out well because we only need one board to do this. We just have to connect GPIO pins that we're going to use for our software SPI, and we'll connect those to the hardware-defined SPI pins. You guys with me? And then we can run it and test it all on one board. The board can initiate a transaction, and then it can be its own slave. Okay? So how do we get started with this? Well, I mentioned last time that SPI generally runs its bit rate is slower than the clock rate. How much slower? Well, I think the example I showed last time, it was 4 times slower, right? So 1 bit was transacted every 4 core clock cycles, right? Now that's going to be tough because remember that every clock the processor nominally executes 1 instruction per cycle, right? So if you're running SPI at a high rate where you're sending 1 bit for every 4 cycles, that only gives you the capacity to execute at most 4 instructions. So obviously we're going to have to run it slower if we want to implement software SPI. What's the slowest we can run it in? Well, if you look at this table, so there's in the SPI control register, there's these data rate bits. There's 2 data bit rates. Well, there's actually 3 data rate bits. 2 of them are over in the control register, and then there's a 3rd one called SPI2X that's in the status register, which is like a double speed mode. But this gives you the ability to go from sending a bit on SPI every 2 cycles all the way down to sending one every 128 cycles, right? But that, I didn't know. I assumed that when I first saw this that was for both the master and the slave mode, but as it turns out, this only applies to when you're a master. If you're a slave, it'll adapt to whatever clock cycle, whatever clock speed it's given as a slave. You guys with me? So these bits are don't cares in slave mode. It doesn't say that anywhere in the data sheet, but I found it out just through experimentation. So the idea would be for us to drive the clock in our software, and then we're going to loop back to the slave interface, and it'll just adopt whatever cycle, whatever clock speed is being driven by the software, right? The SPI hardware, right? So initially I thought, well, why not try to just go at the lowest speed as shown in this table, which is 128 times slower than the core clock. That make sense? So how do we, first of all, I guess the first question is, how do we generate a clock in software? Anyone have any ideas? Well, so you're going to have a GPIO pin that is going to serve as your master clock, and so you basically have to set it high and then set it low, but you have to do that according to a fixed period. You could do that just in a loop where you set it high and then use the wait. There's a wait function called _delay ms. I'm assuming there's also an _delay us as well. And so you could set it high and then have it wait, just do a busy loop, busy wait, and then drive it low, do a busy wait, and then repeat. But that's not a good way to do it because you can't be doing anything else in you only have one processor core, so you can't have the software do anything else while it's doing that. So that's not a good way. It's not a very efficient way to handle it. The other way is to use the timer. And we've talked about the timers before. We've got these 3 timers. One of them is a 16-bit, actually timer/counter. One of them is 16 bits. The other 2 are 8 bits. They can be used for counting cycles. They can be used for doing delays and waits. They can be used for counting external events. They can be used for pulse width modulation. So they're pretty versatile. You can also set them up to run relatively slowly compared to the main system clock by using a clock divider, where you can have them, tick up once every cycle or once every 1,024 cycles, for instance, or anywhere in that range, right? Obviously, in this case, if we want to, we're talking about dividing the clock by 128. We probably don't want to use the clock divider, right? We'll just have the counter tick up once per cycle. Okay, so we can use the timer for that. So we can set the timer, we can have an interrupt, and every time the interrupt fires, then we can toggle the clock. You guys with me on that? That way, we could be doing other things in between these interrupt events. Although, probably can't do too much because we only have, we're only going to have, we're going to divide the clock by 128, right? But the problem is that we have to set the clock high and we have to set the clock low, which means that our interrupt is going to have to fire twice as fast as the clock rate. So it'll be firing every 64 cycles because basically the interrupt has to fire on every rising and falling edge of the clock. So the interrupt will fire every 64 cycles, and so you would have to, this interrupt happening every 64 cycles, and then you have some code that's executed to handle the interrupt. So, whatever time is left over is what, is what you can use to do other things. Of course, now we can also run it slower. I didn't find out that you could even make it slower than that until later, but I just use this 128 as kind of a guideline based on the master description. Okay, so let's go over to the code. All right, so I've got the boilerplate code set up that includes the get char and the put char routines, as well as the init function, which we gave you, that sets up the hardware UART. So as it stands, I've got it set up where I can do prints, because this is useful for debugging, right? You guys with me? Okay, so the first thing I want to do is decide which pins I want to use for my software SPI. So I'm going to do pound defines for those. And so I've got, how many pins do I have to define? Well, it's 4, right? There's MOSI, MISO, SS, and S-clock, right? So I need MOSI, MISO, SS, and S-clock. Okay, and then now you look at the board, you've got ports ports B, C, and D. I've sort of picked up the convention, and I don't know if this is the best way to do it, but I've sort of picked up this convention where if I need a digital pin, I usually use the D port first. I don't know if that's how most people do it, but notice that the C port. Well, hold on. Let me bring up the pin out here. Okay, so these are the D's here in the lower right-hand corner, PD. The B's are above that, and then the C's are over on the left-hand side. The hardware SPI is actually in the B's. B5 is S-clock, B4 is MISO, B3 is MOSI, and B2 is SS. And then the C's, you've got your I²C, and they're on the other side of the board. So I just picked D. But keep in mind that the hardware UART uses D0 and D1. So you want to stay away from those. Even though those are pins on the board, these are also connected to the USB bridge that bridges the UART and the USB. These are shorted together, right? So even though you might say, well, I mean, can I still use, can I use PD 0 and 1 and still use USB over UART over USB? Possibly, but I wouldn't risk it. I would just stay away from those two, right? Because then you risk screwing up your UART connection. So I'll start with PD 2, and I'll go up to PD 5, right? So you can define port D5, port D4, port D3, and port D2. Make sense? And then on the board, I don't know if you can see that in the back, but I just took wires and I connected to the B's. Yeah, so I don't know if I'm using the same pin out here as I did originally, but let's see. I've got it doesn't really matter, but let's see if we go here to the pin out. So S clock, I would connect in this case B5, which is actually pin 13 on the silk screen on the board, right? that would have a wire that would jump down to the clock that I'm using on D, which in this case is D2, which is pin 2, right? You guys with me? And then you do the same thing for MISO, MOSI, and SS. Now with UART, there's a receive and there's a transmit, right? So on one side, your transmit is going to be connected to the receive on the other side, right? So you have to kind of flop the two sides, right? Transmit maps to receive, receive maps to transmit. But in SPI, you don't have to do that because it's kind of neat. You know, you have a master and you have a slave, and you have a master out, slave in, and that same signal, MOSI, is connected to MOSI on both sides because it's understood that one side is the slave and one side is the master, so you don't have to worry about flipping the wires. Yes?
For part D, do we need to like hook up like a port to like the TX on the boards, like since that's what we're writing like the software for?
Yeah, the nice thing is when you test this, when you test part D, you're going to test it by plugging it into a PC running Linux, you know, using the terminal in Linux. So you can configure the same two pins as GPIO and not touch the UART hardware, right? So because these pins can be GPIO or they can be connected to the special purpose hardware interfaces, right? So if you configure these pins as GPIO, they're still going to be connected to the USB bridge, and then so when you have that plugged into your workstation, you'll be able to see, if things are working, you should be able to see characters that you generate from your software. The problem that I had was I can't do that with SPI. I used to have a little device that was an SPI to USB bridge, but when we moved from Swearingen to Story it, we lost it.
Well,
so
I wish you'd have reminded me. I guess I have one.
Oh, okay.
I use mine.
I thought about trying to get it overnighted and stuff, but then I thought, well, I've got one. It's on the board. I can just, you know. So in this case, this is a little bit different than Part D because, and that's a good. I'm glad you brought that up because I'm just going to pick out 4 random pins on here, and I'm going to plug them into the hardwired. And then so I'm going to have the board talk to itself. The board will be both a master and a slave. The master will be the software and the slave will be the hardware. Okay. Okay, so I've got my pins defined. Now I need to set up my my pins, my GPIO pins. So I'm just going to add that to the end of this init function here. So what's the name? How do I set a pin as an input or an output? You use DDR D, right? Port D, DDR is data direction register, D is port D, and I am going to set that up with a 1 means output, right? So what are my outputs? S clock, SS, and MOSI, right? So MOSI, SS, and S clock. And then I will have an input, and I don't think I actually have to do this because this register should come up as all zeros by default, but just to be safe, I am going to set my MISO as explicitly as an input by having that bit set to 0. Okay, you guys all see how I did that? So these 4 symbols are pound defines. They're macros, and the preprocessor will make MOSI port D whatever, right? Which itself is a macro that will. Basically, it's a recursive macro because MOSI is a macro that macros to another macro, and that macro will macro to the actual pin number. Okay, so I've got my pins set up. So the next thing I want to do is, the other thing I might also want to, I mentioned I want to use the CPOL 1. So what does that mean? I need to initialize my clock to 1, right? The clock should be 1 by default. So I can go ahead and drive that right now. So I'll say port D equals port D S clock, and port D equals port D ORed with SS. So that way I'll set my clock and my slave select to high as soon as I get done initializing the pins. Okay, the next thing I want to do is set up well, I have a choice. I could set up the slave SPI connection, or I could set up my timer. I'll go ahead and do the slave first. So the SPI control register, there's only one, which is nice. There's one control register and one status register, which makes this pretty easy compared to like the timer where there's 3 different control registers in there. So what do I want to turn on? Well, first of all, the name of it is SPCR. So SPCR equals SPCR ORed with. Okay, so the first thing I want to set is interrupt enable. I want that. I'm gonna have interrupts for both the SPI and the timer. That way, my software will send something out driven by the timer interrupt, and then the SPI slave will read it in driven by its own interrupt. So I'm going to set the interrupt enable, which is SPIE, and then next is the SPI enable. I need to obviously turn that on. That's actually is what's going to make the pins, the pins on port D that are assigned to SPI, that's going to connect them to the hardware as opposed to the software, right? So this will disconnect those pins from being those 4 pins from being GPIO and make them connected to the SPI hardware SPI. So SPE. Next is data order. I'm going to use the most significant bit first because that's what the accelerometer uses. So I'm just going to leave that one 0. It should be 0 by default. Master slave select. That should be a 1 to make it a slave. Although it's not shown in this slide, but if you look at the data sheet, it says that that's how you set it up as a slave. So what is that? SP. I already forgot what the name. What the MSTR. MSTR. And then anything else? Clock polarity, clock phase. I want those both to be 1 as well. So that'll be CPOL and CFA. All right, that should do it. The last 2 bits are the speed, and initially I set those up to be the F oscillator divided by 128, but I later found out that you don't have to do that. That's only needed if you're a master. Okay. All right, good. So that's set. Now I have an interrupt enable. I have an interrupt for this, so I want to set up my interrupt too. So I'll add that here to the, let's see, where can I put that above init. So ISR. Okay, now I need the ISR name. Well, I don't know what that is. But that's in lib, user lib AVR include AVR M328P. No, sorry, IOM 328P.h. Yes. And then I do a search for SPI. Hopefully it has SPI in the name. Yes, there it is. SPI STC VECT. I don't know what the STC stands for, but I'm assuming that this is my vector. That'll trigger whenever I complete an SPI transaction. Okay, now what's going to go in there? I just basically I just want to print out when I receive something. I'll just print it. That way, on the slave side, I'll print when a transaction has been completed, which will be an 8-bit word that was sent to me by the master. And then on the master side, after I finish, I'll also have an 8-bit word that was sent by the slave. Okay? So I'll just do print, printf, slave, received, data, and then I'm going to do 0x because I'm going to print it in hex. And then I'm going to go %02 capital X, which will that'll format it with it'll pad it out with zeros. It'll allocate 2 digits, and the capital X is hex, and it'll be capital letters for A through F there. And I think that's all I need for that. Okay, so that's done. If you read the behavior of the slave, oh, sorry, I forgot the actual word that I want to print, which is in the data register. Sorry, yeah, that would help. So the SPI data register is the, and I never remember this, wrong slides. SPDR. So I need to add SPDR. There we go. Okay. Any questions about that? Okay. Okay. What's next? Well, I need to set up my timer. Now remember, there's 3 timers. Timer 0 is 8 bits, timer 1 is 16 bits, and timer 2 is 8 bits. I generally use, I favor timer 1, timer counter 1, because it's the 16-bit one. But they all work the same. So in my init function, I want to set that up. Let me bring up those slides, which are back in lecture 1. So there's a couple ways you could do this. The timers have 2 interrupts. There is an overflow interrupt. And so you could, if you wanted, now the timer is going to overflow once it reaches 65,536, which is 2 to the 16th power, right? At least timer 1, right? Because it's a 16-bit timer. You could initialize it to be that number minus 64, or however many cycles you want to count, and then you can trigger on the overflow, right? Or you can alternatively set a compare value, which will trigger interrupt whenever the timer reaches that value, right? And so I already showed you the first way, so I'm going to use the second way now, just because it's something that's a little different. The timer. Let's see, I gotta scroll down here till we get to timer. Here we go. So the timer is kind of complex. As I mentioned, there's 3 control registers: TCCR 0, 1, 2, 3, A, B, and C. The timer has this mode, this CTC mode, which, oh, by the way, there's a register called OCR that allows you to set up your compare value. What value you want to compare to it. The CTC mode is supposed to reset the counter back to 0 whenever you hit your compare value, right? I could not get that to work. It just wouldn't work for me. It just wouldn't reset. It would work. The compare interrupt would trigger, but it wouldn't automatically reset back to 0. So I had to do that manually, right? So. But that's okay, because you can do the reset in the interrupt handler. So once you hit the top or the compare value, you can just have it reset. So there's so TCCR0A allows you to set up the pulse width modulation mode, and it also allows you to set up the output if you want to actually have the timer manipulate an output pin. We don't need any of this. I added this slide because I thought we'd need to start using these bits, but for what we're doing right now, we don't. So you can skip the control register A. Control register B is for the setting up the speed. The default is all zeros, but if you have it set up with all zeros, there's no clock, so the timer's just dead. So I need to put a 1. I want to set the no prescaling, which is to put these CS1, 2, 1, 1, and 1, 0, which are the 3 least significant bits need to be set to 1. So I'm going to go ahead and do that. So TCCR1B, TCCR1B is going to be set to 1. And I'm just going to put a 1 in there. I don't have to shift it because it's in the least significant bit position. These two guys I can leave as 0, and these two guys I can leave as 0. Okay, and then there is also a TI mask, which always confuses me because it's, for all practical purposes, this mask is a control register, but it's not one of the 3 control registers. So it's TI mask, and this allows you to set up the overflow interrupt, or there's actually 2 compare values that you can have it look for while you're counting. And I'm going to use A. So I want to set OCIE0A. So in other words, I'm not going to have it interrupt when it overflows, but I am going to have it interrupt whenever it hits the compare value. So that's TIMSK. And the other thing you want to watch out for here is make sure you have the right number there. This is counter 1. I've made the mistake where I put a 0 there because I was reading it from the documentation and I was reading under the the counter 0 section. So that's going to be a 1 shifted by OCIE0A. OCIE0A. All right. Okay, so the interrupt is set up. And finally, I have to set up the compare value. And that one is, I don't know if I have that in the slides. I might have forgot to add that to the slides. Yes. So I have to add that. I have it written down here somewhere. It's OCR1A. OCR1A. And I'm going to set that to 64. Everyone with me? Yes?
Can you just scroll back over real quick to the port declarations? Would it be so all the way at the top?
Oh, sure, yeah. I'll put this code on the website too, by the way, just like I did the last one. Good? Okay. All right. I think we're all set. Okay. So now I need my interrupt handler for the timer. And so once again, I need to look that up. So what do I search for? Timer 2. Ah, there it is. Timer 1 capped vec? No, comp A. Timer 1 comp A vect. All right, so I'll copy that and paste that here. Make sure I got that right. Yeah, timer 1 comp A vect. All right, and then at the beginning of my main function, I need to make sure that after I call init, I will I'll enable interrupts. Okay, now we're all set. Now we just have to fill in the guts here. All right, so how do we want to set up the interface for the user? Well, the first thing is we need to do a little planning. if you look at the timing diagram for SPI, you can see that you go through this, predefined sequence. You drop the slave select, and then you're going to wait a cycle, SPI cycle, which in our case will be 64 clock cycles of the CPU. And then you're going to drop the S clock, right? And you'll also start sampling data not on the first falling edge of S clock, but on the second falling edge, right? So what this means is you've got sort of a state that the software has to be in for every half cycle, right? So you can declare a global variable called SPI state that will be 0, for instance, when nothing is happening. And then when you initiate a master transaction, you can increment that to 1. And then every time you get an interrupt, a timer interrupt, you can continue incrementing that until you get to the last half cycle, which it turns out, obviously there's 8 bits, and so you need to send, there's going to be 16 half cycles to send those 8 bits. And then there's an extra cycle at the end and at the beginning. So there's actually 18 states you have to go through. So we'll start out with 0, we'll tick that up to 17, at which point we're done, and then we can go back to our idle state. You guys with me? Does it make sense? Now you might say, why do you need to define a global variable? Well, keep in mind that we're gonna have the timer interrupt triggering on every half cycle, and when the timer interrupt triggers, it really has no, you call the function and there's no input parameters, right? It doesn't really know what it's doing, what it's supposed to be doing. So by having a global variable there, you can keep track of what's going on and how far along it is in this SPI transaction, right? So also, by the way, we also need we need to be able to keep track of what we're sending too, right? The data that we're sending out. And remember, SPI is an exchange. So we need to keep track of what we're sending out, but also what we're bringing in, right? So we can have global variables for those as well. So I called them, I'll declare those up here at the top. So UN8_T, I will have SPI state, which I'll initialize to 0, and then UINT8_T will have SPI data and SPI data incoming. Make sense? Then we can have a function called SPI send, which will not be an interrupt handler. This will be the actual interface for the user to send something out. And the input here will be the word. I'll call it word. And the only thing it needs to do is put the word into SPI data and set SPI state to 1. So this should, by setting the state to 1, it's going to get the ball rolling, and it'll make it so when the timer interrupt is called, it'll start sending, and it'll keep incrementing that SPI state until it gets to the end, and then it'll be back to 0. It'll roll back to 0 and stop. Okay. All right. Okay. Any questions so far? Okay. And then over here in the timer interrupt, I am going to assume, now this might not be a great idea, there's probably a better way to do this, but I'm going to assume that this timer interrupt is just always going to fire, whether you're doing, I mean, I shouldn't say assume. It is going to do that based on how I have it set up. One option would be to disable the timer interrupt whenever I'm not doing an SPI transaction. Another option is to just start out this thing with an if statement that says if SPI state doesn't equal 0. And that way, if I'm not doing an SPI transaction, it will still call this guy, but it'll just, it'll just return. It won't do anything. Right? Okay, let's see. Okay, great. So what do I need to do in here? Well, there's 3 things. I need to control the clock. I need to control the data in and the data out. Oh, by the way, I forgot two things over here in my send routine. When we send, in addition to doing this, I want to reset the timer, the counter, to 0. And I want to reset, I want to set the slave select low. I want to initiate the slave select. So port D equals port D or with 1. And actually, I don't want to set it to 1. I want to set it to 0. So I want to do this, which will drive it low. You guys see that? So by setting the counter to 0 and then dropping the slave select, that means that I'm not going to have anything else to do for a 1/2 of a SPI clock cycle, right? The timer interrupt will trigger in 64 cycles, and that will give me this period right here from between when the slave select falls, that's when I call SPI send, right? And nothing will happen until the timer interrupt triggers, which will be in a 1/2 clock cycle, which will be on this falling edge of the clock, right? So the clock will still be high, right? Because I set that high. I initialize that to 1, right? So the first time the timer interrupt triggers, after I drop slave select, I'm also going to drop my clock. You guys with me? Okay. So over in the timer, I need to drop my clock. Now the problem is that I have to keep track of whether I'm going to be, obviously the first time I call it, I'm going to drop the clock, but then on the next time I'm going to raise it. So one way to do it is to just say if the SPI state ANDed with 1, meaning this is a bitwise AND, so this will just determine whether this is a condition that is checking to see if the clock is even or the state is even or odd, right? So the first time I call this, my state will still be 0, and so it'll be even. So it will end up doing the else block. So I'm going to set port D equals port D and with not SS. Okay, so this will set the clock to be 0 whenever the SPI state is even. Make sense? Right? Likewise, I'll set it to 1 whenever it's odd. So this will give me my clock. Port D equals port D or 1 SS. Okay? Yes?
When does the even one trigger? Because isn't that within the first if statement of not equal to 0? So if it's not never equal to 0, it's never going to be even?
Well, oh, sorry. Yes, you're right. I'm sorry. I'm off by 1. Yeah, actually, these should be swapped. Yeah, that's a good point, because the first one will be 1. Right. Yeah. Thank you. I see what you're saying. Yeah. Yeah, because if it's 0, see, it's actually, the first time it's called, it's already going to be set to 1, because that's what the SPI send function sets it to 1. Yeah, thank you. There we go. So this says if it's odd, then I'm going to drop, because the first time I see this, it'll be odd, right?
No,
right?
So the first if statement, you're saying it's not equal to 0. So if it's equal to 0, it's just going to skip that second if statement, so it's never going to be even.
It'll skip the whole thing.
It can be 0 and 1, or it can be multiple numbers.
If it's 0, it's not going to do anything. It's just going to leave the clock high, right? The first time it's called, so the way it'll work is, as a user, I'm going to call the SPI send. That's going to set SPI state to 1, right? So then, and it's also going to reset the timer. So that way, 64 clock cycles later, the timer interrupt will trigger, as it always does. And when it does, it'll see SPI state being 1. So it'll go inside here, and then this if statement will say, are you odd or even, right? So in this will say I'm odd, right? So if it's odd, it's going to do this statement, which is to drive the clock low. So this will be the first falling edge of the clock.
So when would
Right.
it be even? Can SPI state be 0 or 1, or is it?
Oh no, I'm going to increment. I just haven't got to that point yet. Yeah, in fact, I'm going to do that right now. I'm going to go ahead and
That's not all.
yeah, no, I just haven't got there yet. Let's see. So SPI state, I'm going to increment it. I'm also going to check to see if SPI state equals 18, then I'm done. So I'm going to reset it to 0 at that point. And now I'm done. Also, I'm going to print what I've got. So I'm going to say master received 0x %, 02, capital X, and this will be my SPI data incoming. And then I'm going to set SPI data to SPI data incoming, and then I'm done, right? But I've got more stuff to do before that. Everyone okay with that? Okay. Moving on. So when do I actually transact data? That's going to happen. So remember, the first time I call that will be on this edge. But if CFA is 1, that means I'm not doing anything with the data until the following edge. You see that? Why? Because the purple arrow says so. Right? The purple arrow says once you get that first rising edge, right? So when I get the rising edge, at that point my SPI state will be even because I'll have incremented it to 2 by that point, right? So now, whenever it's even is when I'm going to do my thing, right? Transfer the data. So I'm just going to embed that into that same if statement, which is here. Okay, so how am I going to get data? Well, I got to send data and I got to receive data. Let's do receive first. So I'm going to have SPI data incoming equals SPI data incoming. Now, I'm doing a shifting 1 bit at a time. Which bit am I shifting? Well, I'm sending the most significant bit out, and then I'm getting a bit in, and it's going to go into the least significant bit position on the master side, right? Because it's a shift register. So I'm going to take SPI data incoming, I'm going to shift it 1 bit to the left, and I'm going to add the bit that's coming in. Which bit is coming in? Well, I'll have a uint8 type incoming bit, and that's going to be port D shifted to the right by MISO, which will put the MISO bit in the least significant bit position, and then I'm going to also AND that with 1, so it'll just retain the least significant bit. You guys see that? Right? So I'm going to shift it. I'm going to shift the MISO bit down to bit 0, and then I'm going to mask it off. And then I am going to OR it with the incoming this guy. So I'm going to capture the incoming bit in a variable, and then I'm going to just merge it into my SPI data incoming, and I'm going to shift all the bits that were in there before to the left. So I'm going to be moving bits in from the right to the left. Make sense? Okay, what about the outgoing data? Well, I'm going to have a uint8 type outgoing bit. This is going to be in my SPI data register. And I need the most significant bit from that. So I'll just, let's see, I'll shift this 7 bits to the left. Sorry, 7 bits to the right, rather, which will take the most significant bit and move it down to position. Actually, yeah, that's fine. There's a better way I could do that. But and then I will set port D equals port D. Oh, I gotta, here, this part I always make this mistake. So once you do that, you have to have an if statement, because when you set a bit to 0 or 1 in a GPIO, you can't just, I don't know of an efficient way that you can just include that in an expression. So I always just say if, I know that was a bad explanation, I'll just show you what I mean. I say if outgoing bit, in other words, if that is true, if that's asserted, then I will say port D equals port D, or with 1 MOSI. That'll set it to 1. Else, I'll do the alternative expression, which will AND it with the complemented 1 shifted by MOSI, which will set it to 0. You guys see that? So my outgoing bit is the most significant bit in SPI data, and based on what that is, I'll either set the corresponding pin to 1 or 0, right? And then I will have to also shift my SPI data to be SPI data shifted to the left by 1, because I'm going most significant bit, so I'm going from left to right here. You guys see that? All right. Did I take care of everything? Make sense? So to actually use this, in my main, I will, after I enable interrupts, I'll just say, I'll have to set up the SPDR. So my SPI data register, which is on the slave side, will have a value set to exchange with the master. So I'll make that DE. And then I'll just do an SPI send with a value of AD. And then I'll just go into an infinite loop. Okay, so initialize, enable interrupts. I'm going to put DE on the slave. Then I'm going to send AD on the master. What should happen if this works is the SPI interrupt will fire on the slave side, and it will say, I received AD. And then my code that I wrote in the timer interrupt down here should print a message after it finishes sending that it has received AD from the slave, right? So they should exchange the 2 bytes. Make sense? Data, SPI data incoming. Just double check these names. SPI data incoming, that's the incoming bit. Oh, yes, one thing I made, I'm glad I caught this. Notice this, port D. That's wrong. Port D is only used for outputs. Should be pin D for inputs. Right? I had forgotten about that because it's been a while since I've done inputs. So I normally do outputs, right? I use port D, but it should be pin D. Okay, so whenever you use input, you use pin, output is port. So this is pin D, shifted to the right by MISO, mask out the 1, put that in the least significant bit position, shift the other incoming to the left 1. Outgoing is port D, and that's MOSI, output master out, and then the SPI data is shifted to the right. So once this is all done, SPI data should be gone. It'll be all shifted out. And I'll have received another byte in incoming. I'll take the incoming and put it on SPI data for the user so the user can access that as a global variable. I probably could have just had him use, or he or she use incoming. I don't know. I'm double buffering it like they do in the hardware, which is why I have two buffers, and then they get merged after the transaction is complete. Sound good? Okay. Let's do a make. Oh wow, that did not just work. I don't believe it. Is that the right? I always get. Oh yeah, that's why I didn't save it. I knew it. Oh no, it worked. It still worked. Oh wait a minute. I don't believe it. I must be in a different directory. Downloads lab UR. Downloads lab UR. Is this really the same file? Main.c? Oh, it is. Look at that. Wow. I mean, that might be the first time my first compile worked. Well, we'll see if it actually works. I got to plug in. Okay, so I've got both the UART and the programmer plugged into this little hub. So that way, okay. Okay, so now I got to do ls USB, make sure this guy is connected. Atmel ICE debugger and the integrated My Smart USB Lite. Looks like that worked. Now I have to do a change mod 777 dev bus USB 001 009. All right. And then over here, I'm going to do sudo pico com -b 57600. Whoops. Dev tty USB 0. All right, and then we're cool. Sudo make burn. Yeah, Charles found the secret to making that fast, but he didn't propagate that out to you guys. So only we get to use that. No, it's actually quite easy. In the make file, if you, under the burn section here, under the burn rule. Oh, I actually don't even have it in. Oh, that's interesting.
So it saves it inside of the programmer's flash. So
Oh.
you only have to do it once, and then it remembers forever.
So I believe it's P1, or is it
Big B1?
B1, yeah.
Yeah.
So B1.
See, this is why you should pay attention in lecture.
Yeah, so,
Deep magics get shared here.
okay, so make burn. Okay. All right, so, so the good news is the UART's working. It printed the slave message and the master message, which means it didn't work completely, but it does show the fact that those both printed means that the SPI interrupt fired, so the SPI slave hardware recognized that a word has transacted, so that's good news. The fact that the master printed its message means that the timer interrupt is working, and it means that also my SPI state is incrementing as it should be from 0 to 18, right? And it only printed it once, and it should have only printed it once because I only do one transaction, then I go into an infinite loop. Yes?
Would you mind to remind me the reason for the 0 to 18?
Oh, because there's 18 half cycles inside the timing diagram. So it has to go through 18 invocations of the timer interrupt. All right, you can't do it once per cycle because you're driving the clock with the timer interrupt. So you have to go half cycles because you have to say clock low, clock high, clock low. So you have to call that interrupt handler twice per cycle because you got to set it, rising edge and falling edge. Right? Okay, so everything worked except I didn't get what I expected. I got a 0 received from the slave and an FF received from the master. So I have a bug in there somewhere. So one of the things I just realized I forgot is I mentioned earlier in the lecture that the timer will not reset itself. So inside the timer interrupt, it's important that you set t count 1 to be 0. You have to reset it manually. There's a mode called CTC mode that's supposed to do that automatically, but I don't know what I'm doing wrong. I can't get that to work. It's just a bit, if you read the manual, it says there's a bit you can set in there, and I don't know, it's not working for me. So it's fine though. You can just reset it manually inside the interrupt handler. Okay. I don't know if that's the problem or not, but we'll find out. Make burn. Okay, it looks like, did I get something there? It's hard to tell. Yeah, okay, didn't work. Still same thing. Okay, so next thing to check here is to make sure I used it properly. So I set the data register to DE. I sent AD. Okay. Obviously, interrupts are working. Okay, now the problem is, let's see. It's interesting that both sides aren't working. So I've had cases where one side worked and the other didn't, right? But they're both, so that means that I'm probably got something switched here. See, let's just check here. DDRD, I've got the master out slave in. Is an output, as is the SS and S clock. Remember, outputs are 1 in the DDR data direction register. Inputs are 0. The MISO is an input, so that's set up properly. The S clock and the SS are both set to 1. Oh, did I raise SS? Oh, yeah, okay, that would be it. So, sorry. So when I'm done with my transaction on the master side, I have to deassert the slave select, right? Forgot to do that. So port D equals port D and, or with 1. There we go. So I got to bring the slave select back high when I'm done. This is all the cleanup code here, right? So SPI state 0 kind of turns everything off. This will unselect the slave. Good. Am I getting, I can't tell if I'm actually getting data over there. Hold on, let's go. Let's kill that. Yes. Okay. Yeah, I'm still getting 0. Okay. All right. Let's keep debugging. Okay, so slave select is fixed now. SPI state gets reset. I print that message. SPI data incoming gets set. Over here, I've got port D. So this is the state. This should be, well, that's a problem. That should be S clock there. Sorry. All right. Yeah. Sorry. Yeah, that would be it. Yeah, so inside the timer code, I'm toggling S clock, not SS, right? I got that for whatever, I got the wires crossed in my head. So that should be S clock is the one that's being toggled there.
Does that mean you have to change the F1 in SPI state equals 18?
No, that was right. Yeah, the slave select is normally 1. When I call SPI send, it drops it to 0, and then once the SPI state gets to 18, when you're done, you raise it back up again. So it gets set to 1 in here, and it gets set to 0 inside my send, which is up here at the top, right? SS, right? Likewise, it gets set to 1 at the beginning in the init function, I think, right? Then I set it to 1 in init, yeah, right here, right? So it gets initialized to 1, Gets set to 0 when you send, gets set to 1 when you finish the transaction. The clock, on the other hand, is set at 1 initially because I've got my polarity as 1. And then the clock is toggled inside of this. Every time you call this timer interrupt, you're going to toggle the clock, which is your S clock, right? There we go. That's different. Okay, so master received FF and received data 5.6. That's interesting. Did I get the byte order wrong? 5.6. 5.6, and it's supposed to be what you received. It's supposed to be DE, right? It's supposed to be DE. D is 1101, and E is 1110, right? I think it's DE. I sent DE, well, because it's DEAD. I'm spelling out dead beef. So it's the master has DE, and the slave should get DE. The master should get AD, right? So the slave is going to get what the master sent it, which was the first two characters, DE, right? So DE, so let's see. So actually, I thought maybe they were backwards or something, but 1100. No, that's just totally goofed up. All right. See, what did I screw up here? So I've got the master. The master received all ones. That's also a clue. So all ones. So pin D. So incoming bit. Incoming bit ORed with SPI Data Incoming. SPI Data Incoming is not initialized, but it shouldn't matter because whatever was in there prior will have been all shifted out by the time I get done with this. So that's okay. SPI Data, on the other hand, does get initialized by the SPI send up here, right? SPI Data gets set to Word. SPI state gets set to 1. T count gets reset. Port D gets set with SS. Get char. This guy is SPDR. Gets triggered. T count. Let's see. Reset the counter. We check the SPI state. We drop. Make sure I got the phase here correct. So the first clock edge. This is the falling edge, and just double check this, the one I had working earlier. So if it's 0, oh, interesting. Let me switch this. This will just change the clock edge that we sample on. Okay, well, there we go. We got the that fixed the receive data. Is AD. Actually, the master should have had slave. Let's see, DA, AD. The master should have had AD actually, right? Unless. What's that? Oh, that's a good point. Yeah, I didn't notice that. I just assumed that was what was left in the buffer. But you're right, it is firing twice. So that's got to be a timing issue. SPI state. Yeah, that the only reason that would be is if the slave thought that it was receiving two transactions, right?
If you're getting an extra bit.
If there's an extra bit, yeah. Yeah, exactly. So it could be that, am I going too many on here? Okay, well that's interesting. So by doing that, it gets rid of that. It gets rid of that second interrupt from the SPI slave. What did I have in the? So I have a version of this that's working, but it's obviously there's differences because I wrote this from scratch.
Is your interrupt getting called through really?
No, it shouldn't be. I reset the counter, check for active SPI. SPI state, just say greater than 0. I don't think that matters. If SPI state and 1 equals 0, then I toggle the clock. Shift data out. So this sets the clock to 0. This sets it to 1. This will set my master in, slave out. There's an incoming bit there. We OR that in. The SPI data incoming gets shifted to the left by 1 bit. So I've got that set the same way here. Incoming gets shifted to the left by 1, and you OR the incoming bit. The incoming bit is pin D, shifted right by MISO and 1. Yep. And then the data out is port D, SPI data shifted to the right by 1. Right. Something subtle. Now, when I was debugging this originally, I had the advantage of having my the logic analyzer, which I had to use extensively to get this to work. But now I'm just doing it based on whether it works with the slave interface.
I suppose we probably have to show how to use those.
I had to use it. Yeah, I had to use it. I would have never got this working without that.
Do we know what we're going to do so that they can get to it in off hours? Because we're supposed to leave it locked up. And so
Not necessarily. I would just unlock it.
Sure, I guess we can just take the probes out.
Or take the probes out. Yeah, yeah.
'Cause I think Ryan has other stuff in there other than just our probes. So
Oh, okay. When that's the case, we could just take them out.
yeah, that's reasonable.
SPI state plus plus. If it's 17, we bail out. I don't see the issue, but it's got to be something obscure. Master receive 1 1. So one of the issues is I'm getting all 1s for data incoming. So that might be. I'm not sure, but I will. Whatever it is, it's minor. I'll fix it, and I'll send the fixed version out and let you know what it was. Yes.
So for part D, taking this like code and looking at it and then like comparing that to the UART. So obviously we don't have to like worry about the SPI and like all that interfacing. But what will we use from this in part D? Is it just the timer part, and then like obviously we don't use SPI like in your timer interrupt, but using that interrupt of the timer, is that like the only thing that we really
Yes.
need to use, and then sending the bit to the TX, just not from hardware?
Right. Yeah. So you don't need the SPI interrupt that I used here was only for the testing. Right. You're going to be testing with the USB, so you won't need that. The timer will give you a way to synchronize. Your timer will be much slower than this one because this one's running at 1/128th of 16 megahertz, whereas they're doing 57,600 baud.
Correct.
Yeah. So your timer frequency, your timer interrupt will be triggering at a lower frequency. Also, you don't have to generate a clock, which means that your timer interrupt only has to activate once per cycle, not once per clock state, right?
Okay, so we don't have to manage a clock. We just kind of like so many seconds.
Right.
Interrupt.
Yep. Yeah. So this is the UART is significantly simpler in that sense than this. But this gives you an idea how to set things up and also how to shift. What I wanted to show you how to shift bits in and out too, which that might actually be where my bug is. But like I said, I'll fix that and I'll let you know what's going on there.
actually the reference version doesn't even use the timer. I just did delay MS, so.
Yeah, or can they do that?
They could. Now, of course, it'll make anytime you do like printf, it'll be like super slow because like it'll block
Yeah.
and all that. So, well, I guess it still blocks anyway because it's not buffered. So.
Yeah, so Charles says that you have the option also to not use the timer interrupt. You could use a loop with a delay. You can just adjust the delay to be 157,600ths of a second.
Timer's more elegant though.
Well, the other reason I use the timer, by the way, here was because in the next lab we're going to be using the timer for pulse width modulation, and you're going to have to be using it for that, and also using that comparison value is part of the PWM. So I was kind of looking ahead to that as well. Right. And of course, the SPI you'll be using for the accelerometer. Okay, great. Well, I'll send the code out once I fix whatever's wrong with it, and I'll see you. We'll see you in lab. Thank you. Hi, everyone. As a follow-up to the demo I did today in class, I wanted to show you the bugs in the code that prevented it from working. It's kind of a couple minor things. First of all, when using the hardware slave SPI interface, you are required to set up port B4 as an output, which matches up to the master in slave out pin. So you can do that by setting DDR-B pin port B4 to 1. And the other mistake I made was in the SPI control register, I set the DORD bit to 1, which I thought that meant that the most significant bit was shifted out of the master side first, but in fact that bit should have been set to 0, and as well as the MSTR bit, which, and this was a little bit more obvious. I mean, if you want to set up the interface as a slave, then the bit that is MSTR, which obviously stands for master, that should be set to 0, and I had it set to 1. So it was those 3 bits that were causing the issue in class today. The version of the code that's available on Dropbox has these fixes incorporated into it, and it does work. So thank you, and sorry for the bugs.